exponential growth and decay problems. Example 1 is about population growth. We're told that in the year 2000, the world population was approximately 6.08 billion, and the annual rate of increase was about 1.26%. Part A asks for the growth factor for the world population. So growth factor is the number 1 plus the rate at which it's increasing. We write the rate as a decimal, so it's 1.0126. Now part B says, suppose the rate continues to be this amount. Write a function to model the world population. So our function will be P for population after T years equals the initial amount at the time of this study, 6.08 billion, times 1.0126 raised to the t power. Part C says, let x, or in our case, let t, be the number of years past the year 2000. Using the model, what was the world population in 2010? So what we do is we evaluate this formula for t equals 10, and we use a scientific calculator at this point, or graphing calculator, and we get that in the year 2010, which is 10 years after the start of this study, the world population would have been 6.89 billion. Next, we'll look at exponential decay. Here we're told a computer, which was valued at 6,500, is depreciating at a rate of 14.3% per year. To write a function that models the value, we want to start with the decay factor. That's 1 minus the 14.3%. Once again, we write that as a decimal. And we get 0.857 for the decay factor. So our formula is the value after t years is $6,500, which was the initial value, times 0.857 raised to the t power. After 3 years, we just want to find v of 3. Using a calculator, we get the value after 3 years has dropped to about $4,091.25. Now we're going to also look at another exponential decay problem. This time it's the population of a species of animals. And we'll see how the graph of this function can help us solve a problem related to exponential decay. So the population of a certain animal species, it says, decreases at a rate of 3.5% per year. So we can start right there with our decay factor of 0.965. We know that there's 80 animals in the initial study. So our P, population after T years, will be the 80, which was in the initial amount, times 0.965 raised to the t power. So we can graph that using any graphing utility or graphing calculator, and we can see that we have an exponential decay function. And we're asked to estimate the number of years until the population first drops below 15 animals. So we want to look on our y-axis. For 15, we want to look across, and we'll see that it's about 47 years that would take for the 80 animals to drop below 15. So now we'll look at a decay problem. Traditional decay problem is about car depreciation. So you buy the car for $12,500 and it depreciates 9% each year. So our decay factor then is 0.91. And what is the value of the car after 5 years? Well, first, here's our function. V of t equals the initial amount of 12,500 times 0.91 raised to the t power. We want to find v of t, and we get that this car, after 5 years, is worth about $7,800.40. Now we'll look at a baseball card, which we're buying as an investment. We bought it for $50, and we find out that it increases by 3% in value each year. So our growth factor in this case is 1.03. Our formula is V, the value of the card after T years, equals 50, the initial amount, times 1.03 raised to the T power. So after 5 years, V of 5, the baseball card is worth about $57.96.